Hey guys, so I've been getting a lot of questions about the ORP. There's a lot of confusion out there. I totally understand it. So I'm going to take this opportunity to walk through some of the chemistry behind what the ORP actually means. Now, remember, it is an oxidation reduction reaction, okay? Oxidation reduction potential. And therefore, you have a transfer of electrons. Now, this all goes back to what's known as the She, or the standard hydrogen electrode. And that's what I want to show you. If you understand this, you'll understand all the other concepts we've been talking about, including why the ORP changes so much as a function of pH as well as other things. So let's just go through this really quick, okay? So first off, let's talk about that half cell reduction potential of the hydrogen ions to make hydrogen gas. Well, let's write it down. So we have H plus, we'll have two H pluses. This is the hydrogen ions. This is what makes pH, okay? pH is literally the negative log of the hydrogen ion concentration or activity. And then plus our two electrons, okay? And then these will combine together and you will make our hydrogen molecule, H2 gas. Now the question is, how much voltage is produced, let's say, if you have the electrons and the hydrogen ions, right, to put them together? Well, it's estimated around 4 volts or so. However, science has arbitrarily assigned this value as 0, okay? So let's write that. So this is arbitrarily assigned as 0 volts, okay? And this is called the E naught. And that means under standard conditions. So standard conditions in chemistry means a specific thing. For example, in this case, you'll have a 1 molar concentration. So for hydrogen ions, a 1 molar concentration means you have a pH of 0, all right? So the activity of the hydrogen ion is 0. And also the pressure of hydrogen gas will be 1 bar. And that is going to be defined as 0. So it's like the temperature scale, right? We define water freezes at 0 degrees Celsius. We didn't measure it and then say that's what happens. Like we define that, and that the whole scale is based upon that. So everything else, all the other redox reactions that are out there, are all based upon the She, the standard hydrogen electrode. In fact, if we go to this table right here, you'll see you have, like, at the top you have fluorine plus 2 electrons goes to fluoride. That has a redox potential under standard conditions of 2.87 volts. All right, so very high. It's very oxidizing. Fluorine is very oxidizing. Same thing with chlorine, right? It's very oxidizing. That one is 1.36 volts for that redox couple. And everything, though, is based or relative to the standard hydrogen electrode, which is why this is in bold, the 2H plus goes to plus electrons goes to hydrogen gas equals your 0 volts. All right, and that's true for everything. Now the question then is, what happens if things are not in standard conditions? Because nobody's drinking a pH 0 water, for example, right? Let's say the pH is 7. Well, that's going to change, right, our reaction here, because in the equation we have two hydrogen ions. Well, if you have more or less hydrogen ions, in this case, we have a lot less hydrogen ions because you have an alkaline pH, then this is not going to be standard conditions anymore. So the voltage potential will be different. Now, you can calculate this by using what's known as the Nernst equation. So let's just go through that quickly, all right? This is just standard electrochemistry a little bit. So the Nernst equation, in this case, you want to calculate what the true redox potential is. So that's E, and that's going to be equal to the redox potential under standard conditions of whatever redox couple we're talking about, all right, minus, we'll have some constants in here, RT over NF. This is going to be the gas constant. The R, you have T for temperature, which can be in kelvins, 298.15 degrees kelvins, and for the number of electrons being transferred, and F for Faraday's constant. And then this is going to be multiplied by the log of, we will write it as the reduced species on top. This is going to be a ratio over the oxidized species. Okay, and then each one will be raised to their specific coefficients that we'll talk about. Okay, so this is your standard Nernst equation. There's different forms of the Nernst equation. This is a more simple one we're going to use. But let's simplify it even more so we can understand what we're talking about when we change things from a standard conditions to different conditions, like the formal potential, right, in our bodies. All right, watch this. So let's just simplify this. All right, so we're going to start with E. That's what we want to calculate. And then we'll go equals our E naught. We'll have to look that up in the table. The E naught you just look up in the table, just like this one we just showed, right? Those are all standard reduction potentials. And then we'll go and do minus. Again, we can multiply and divide all these together, right? Our gas constant times the temperature. If we do all of that, then we will get our 59.16. And this can be in millivolts. We just have to keep that in mind, millivolts. And then we'll times that by the log of our reduced species. So let's look at our equation. Our reduced species is hydrogen gas because that received the 2 electrons. So we put our H2 here. And so this is H2. Well, we have to think, what is the pressure? Well, we're going to just say it's going to be 1. All right. So it'll be 1. So I just want to just put out here, this is going to be the H2 concentration. This was the H plus concentration. All right. And now we can do, in fact, maybe we'll do this quickly under standard conditions so you can really see how this works. If the denominator here with the oxidized one is going to be the H plus ions, and if the standard conditions is 1 molar, so we put 1 right here, and then of course we'd raise these to our coefficients, so raise 1 here, and then this would also be raised to the 1. We have the N. Okay, the N in this case is going to be 2 electrons. All right. So 59.16 divided by 2. Now let's just do this quick math. All right. What is 1 to the first power? 1. 1 squared is going to be 1. So 1 divided by 1 is 1. And then the log of 1 is 0. Well, 0 times this number is 0. And E naught, which we know, we look at the table, okay, E naught says is 0. So we go 0 minus 0 is 0. So that means the redox potential of this is 0. Now let's change the pH and see what happens, all right? Change the pH. So that means this denominator, instead of being just 1, we're going to make the pH 7. So pH 7, you just take the antilog of that, and you would get 1 times 10 to the negative 7, okay? And this is going to be the denominator here, so we're going to have to, we will square this just like we did here. Remember, this number is what we're going to do here, okay? Now, you have to square this, and this is on the denominator. So because this is exponents, we can just multiply this. So this would be 1 times 10 to the negative 14, all right? So now we'd have, I'll just write it here, 1 over 1 times 10 to the negative 14. Ooh, probably not be able to see that very well. Now it's going to be the log of this fraction, right? However, this is negative 14, so we can just move the 14 on top. And so it'd be 1 times 10 to the 14th power. We take the log of that and we get 14. So now let's rewrite this, and we will go E equals E naught. We look at the table. Well, E naught's already 0, so we don't have to write that. Okay, so let's just go equals negative 59.16 divided by 2, and then we just did the log, and that's going to be 14. So we put 14 right there. Now let's put this into our calculator. All right, and what do we get? We get, let's do it really quick. We get negative 400 equals negative 410 millivolts. That's why a higher pH is going to change this so much. So the point of all of this is that the ORP reading, everything is based upon the SHE, the standard hydrogen electrode, and everything is relative to that. And as you start to change the hydrogen ion concentration, which is the pH, everything else is going to change a lot. But you can use the Nernst equation to literally predict what's exactly going to be, as long as you know what the redox couples are. And you can simply plug in those into the equations. And we do this all the time in electrochemistry. So hope that makes more sense. Thank you.